I'm Zheng, and today I'll be presenting our work, WLB-LLM, Workload-Balanced 4D Parallelism for large language model training. And this work was done in collaboration between UC San Diego and Meta. So the training of a large language model is extremely expensive. For example, Llama 3, a 400 billion model, uses 16,000 HR GPUs, and Grok 3 use about 100,000 GPUs for training. And the right figure shows the estimated training cost of some large language model. The largest one, like GPT-4 and Gemini Ultra, takes more than $100 million. So given the high training cost, are we fully utilizing our GPUs in large language model training? Unfortunately, the answer is no. We analyzed the GPU trace from Llama 3 400 billion model training on 8,000 GPUs, and we measure the computation latency on all GPUs. The result shows a 1.4 times gap in computation latency among different GPUs. And this indicates that there's significant workload imbalance among GPUs during LLM training. After identifying the workload imbalance issue, we raised two key questions that we aim to answer. What are the causes of the workload imbalance, and how we can resolve the imbalance? To answer these questions, I will first provide some background on 4D parallelism, and then analyze the imbalance across different parallelism dimensions. And based on this, I will then present our design to address the imbalance issue, and finally share some evaluation results. So let me first start with some background about 4D parallelism. Parallelism basically defines how models are distributed to GPUs. And to train a model with billions of parameters on thousands of GPUs, large language model training leverages four-dimensional parallelism, including data parallelism, pipeline parallelism, context parallelism, and tensor parallelism. First, data parallelism is conceptually duplicate models to different workers. And each worker has a duplication of model and takes its own input batch for training. And after that, the DP worker needs to perform gradient synchronization to correctly update the model. And pipeline parallelism will split the model in a layer-wise manner. And here, each worker gets one layer, and during training, we have to communicate the intermediate result between PP workers. Context parallelism is designed to mitigate the large memory consumption of the activations in long context training. When the context window grows longer, the activation size also increases proportionally and could exceed the memory capacity of a single worker. So to overcome this challenge, the input is sharded and distributed to different workers along sequence length dimension. So the activation size on each worker could be reduced. And lastly, the tensor parallelism splits the model parameters within a layer and distributes the parameters to different workers. When applying the four-dimensional parallelism together, the most outer dimension is data parallelism, and then the model in a DP worker are parallelized by pipeline parallelism. And next dimension is context parallelism. Sorry. The model shard is duplicated, and the input is partitioned and distributed across CP workers. Lastly, the most inner dimension is the tensor parallelism. Now we understand how the large language model is parallelized across four dimensions, and however, which dimension has an imbalance issue and why remains unclear. So to answer it, we performed a more detailed analysis to get the reason of the imbalance. Here we normalize the attention computation latency on each GPUs, and we can see four boxes in the figure. Each is a DP worker containing 2,048 GPUs, and the vertical line in each box is a PP worker which has 128 GPUs. In this figure, we can observe that there is significant imbalance across DP and PP workers. This is caused by the process of input packing. The input packing works as follows. First, at each iteration, the data loader will sample input documents from the dataset. And the document has varying lengths. The figure shows the document length distribution of the training date. As we can see, most input documents are relatively short. There are some extremely long documents within the dataset. So to organize the inputs with varying lengths into regular shaped tensors, we have to pack them together to form macro batches with the same length. Here we have 2 macro batches, one with 2 documents and the other with 4 documents. And after that, to ensure the attention computation is correct, each token only computes attention with tokens within the same documents. So here, we do some attention masking, and the area of each triangle represents the amount of attention computation workload of each document. And as we can see, the blue area is much larger than the yellow area. So this causes the workload imbalance across DP and PP workers. And next, we zoom into a single PP worker to analyze the imbalance at more inner dimensions, like context parallelism and tensor parallelism. So here, each PP worker has 16 CPU worker, and each are marked with a circle in the figure. And each circle contains 8 points representing 8 TP workers within each CPU worker. And the TP workers do not show any workload imbalance since they operate on the same input. But however, there's a significant imbalance could be observed across the CPU workers. This is caused by the input sharding at the CP level. So at CP level, the input macro batch will be sharded and distributed to different workers. So basically, it will be sharded into 2 times of the CP size. So here we have 2 workers, so it will be partitioned to 4 shards. And each worker get 2 of the shards. And the attention computation workload corresponding to each worker is represented in the right part. So as we can see, the CP1 has much heavier workload than CP0. This is the reason of the imbalance at the CP level. So now we have found that imbalance happened at the DP, PP, and the CP level caused by the input packing and the sharding respectively. So the remaining question is how to resolve the imbalance. So next, I will introduce how we address the imbalance issue. First, we want to optimize the packing for the interbatch imbalance. A naive solution could be fixed length packing, which means we keep the fixed context window size and try to optimize the packing to balance the attention workloads across macro batches. So the fixed length packing, in the fixed length packing, the data loader will first load a global batch, which contains documents with varying lengths, and the fixed length packing will pack the input documents into macro batches with the same total length and aims to minimize attention workload imbalance across the macro batches. And this can be achieved by, for example, solving an integer linear programming problem. However, the performance of fixed length packing is not good. When measuring the average imbalance degree computed by dividing the maximum workload by the minimum workload within a batch, the fixed length packing results in a high imbalance degree of over 2. This is because when there is a single long document within a global batch, no matter how we optimize the packing of short documents, we cannot match the attention workload to the single long documents. But what if we load more batches at a time and optimizing the packing across more batches? It could slightly decrease the degree of imbalance, but it also increases the training loss, since the packing reorders the training inputs and enlarge the packing window across more batches could have a larger impact on the randomness of their sampling. So to overcome the limitation of fixed length packing, our solution is to perform variable length packing with outlier document delay. So the variable length packing breaks constraint of fixed context window. And we enable different macro batches have variable lengths. And also, we change the optimization goal from balancing the attention workloads to balance the total computation and communication latency for each macro batch. The key insight here is that besides the attention computation, larger model has other operators like Zheng, element-wide operation, and collective communications. So the latency of attention is quadratic to the document length, but other operations are linear to the document length. So with variable length packing, we can pack more short documents together to form a longer macro batch. So here, the single long documents may have more attention workload, but they will have less linear operations workloads. So it is possible to match the total computation and communication latency to achieve balanced workload. And another optimization is outlier document delay. So rather than reorder all the documents within the global batch, we choose to selectively delay the long documents. This is because long documents have large impacts on the imbalance, but they only contribute a small ratio of the training tokens. So only delaying the long documents could help us mitigate the imbalance while minimizing the impact on the data sampling randomness. When combining both optimization together, our input packing strategy works as follows. So when data loader loading documents from the dataset, the document will be split based on the document length. So the extremely long documents will be added into the multi-layer outlier queue to wait for enough long documents. And the remaining document will be added into the current batch for packing. And when the outlier queue accumulates enough batches for each macro batches, so they will be pop out and added to the current batch. And the batching strategy follows the variable length packing to output the macro batches with balanced workload. And you can find more details in our paper for our packing strategy. And besides packing, input sharding at the CP level also introduces workload imbalance. So traditionally, the packing is in a coarse-grained per sequence manner, which will shard the whole sequence. So some of the CP worker will get much heavier workload than others. To optimize this, we propose to perform a more fine-grained per document sharding. So here we have two workers. We shard each document into 4 shards. And the first worker takes the first shard and last shard of each document, and second worker takes the 2 of the middle shard of each document. So in this case, we can observe that two workers here will get exactly the same attention workload. So it will fully eliminate the workload imbalance issue at the CP level. However, the fine-grained sharding also introduces new challenges, which is the kernel efficiency versus the sharding imbalance. So as we can see, if we apply fine-grained sharding to very short documents, it will lead to many small document shards, which means the Q length and the KV length of the shard is very small. And when we profile the kernel efficiency with different Q length and KV length, it can be seen that if the Q length and KV length is not large enough, the attention kernel could not achieve the peak performance. So to overcome these challenges, we propose an adaptive sharding selection method. We implement a kernel latency estimator, and we will predict the kernel latency of different sharding methods, and we will adaptively choose the CP sharding strategy with lower latency at runtime. So here is a quick summary of our optimizations. We propose variable length packing with outlier document delay to solve the imbalance caused by the input packing, and we propose this per document sharding and adaptive sharding selection to solve the imbalance caused by the input sharding at the CP level. And lastly, let me demonstrate the improvement achieved by our solution. So we test WLB-LLM on different model sizes ranging from 500 million to 70 billion. And the detailed 40 parallelism configuration can be found in this table. And regarding the baseline, we choose 2 baselines for comparison. The first one is the 40 parallelism implementation for Llama 3 training and meta. And the second one is fixed 40, which is the 0.40 baseline plus the fixed length packing optimizations. So first is the end-to-end performance. As we can see, if we only use the fixed 40 optimization, it could only slightly mitigate the imbalance issue. And the improvement is less than 5% on average. While our solution could consistently outperform all baselines on all configurations and achieving 1.2 times speed up on average. And furthermore, we perform more detailed optimization analysis. So first, we test our method on different context window size. As we can see, our method can achieve a higher speedup on larger context window size. This is because under larger context window size, there will be higher probability to have the imbalance problems. And second, we evaluate the optimality and the overhead of different packing optimizations. And our solutions achieve near optimal imbalance degrees, and the packing overhead is also very low, which is about 20 milliseconds per batch. And you can find more evaluation result in our paper. Thank you for listening, and I'm willing to take any questions.